Hi Rockridge, it's Mrs. Berger helping you with your Algebra 2 lessons. This lesson today is about properties of exponents, nth roots, and simplifying radical expressions. Real quick, we want you to remember some of the properties of exponents you have learned in Algebra 1. Okay? You should recall all of these. So a to the m power times a to the n power is simplified as a to the m plus n. So an example of that is a to the third times a squared equals a to the 3 plus 2, or a to the fifth. Okay? So when you see a base to a power times a base to a power, you should add those powers. Okay? It's a multiplication problem, but you add the powers. Power of a power works differently. A to the third to the second power means you multiply those to get an a to the sixth power. A lot of people get those two mixed up. If you have the power outside of a product, let's say we've got a 2a in there, and we're bringing that to the 2 power. You need to quote-unquote distribute that power to everyone inside. So you need to make that a 2 squared times a squared. And we never leave 2 squared as that, right? We always tell Mrs. Berger it's a 4a squared as our final answer, okay? So that's power of a product. And again, you should remember a lot of this from Algebra 1. Anything to a negative exponent, we need to put to the bottom of the fraction. So let me give you a couple examples here. Let's say 2 to the negative 2. You should rewrite that as 1 over 2 to the positive 2, or 1 over 4. A different example might be 1 over 2 to the negative, let's say 3. Whenever you want to get rid of a negative exponent, you move it to the other side of the fraction, so we move that up now instead of down. So we make that 2 to the positive 3 over 1, since there's nothing left down here. 2 to the third is 8. So when you see these, your final answer to me should be either 1 over 4 for this situation, or 8 for this situation, okay? Hopefully we all remember that anything to the 0 power is 1. So 2 to the 0 power is 1. Anything to the 0 power is 1. So anytime you encounter that, you should reduce that to 1. Quotient of powers works very similarly to product of powers. Instead of adding our powers, we subtract our powers. So if we had a to the third on the top and a squared on the bottom, same base, powers subtract. So that becomes a to the 3 minus 2. Well, what's a to the 3 minus 2? That's a to the 1 power, or just a. Or we could exemplify this with a squared over a to the 4th. Think of this as a, we always take top minus bottom, a to the 2 minus 4, or a to the negative 2. What did I just say we do with negative powers? We put them to a bottom of a fraction. So the final written answer for this should be 1 over a squared. Okay? Power of a quotient works very similar to power of a product. You quote-unquote distribute this power to everybody inside. So if you had 2 over b squared, you would make that 2 squared over b squared, or 4 over b squared, okay? So again, hopefully this was a review from Algebra 1, but these examples are really helpful for you to go back and remind yourselves of these power rules. Alright, so our new lesson is about nth root and radicals. Nth roots and radicals. So something to the nth root, or something that is under a radical. We say that a square root radical is simplified, or in simplest form, when the radicand has no square factors. What does that mean? The radicand is the number underneath the radical. The square root is a radical. Anything under here. You can't have any perfect squares left inside. Okay, so we need to be searching in here for perfect squares. Can you think of any perfect squares that are factors of 40? Let's think of the perfect squares themselves. 2 squared is 4, 4 squared is 16. Look for those numbers and find the biggest one that you can. If I look at 40, I find that there is a 4 in there times 10. 4 is the biggest perfect square I can find. If there is a perfect square in there, we can't leave it in there. That is not simplest form. We need to pull it out. Well, how do we pull it out? Well, if we're taking square roots of things, what we're saying is we're taking the square root of 4 times the square root of 10. Well, what's the square root of 4? That's 2. Square root of 10, you can't pull anything else out, so we leave that behind. I kind of call this the perfect pretty number here, and then the trash left behind. Okay? So our simplified form of the square root of 40 is 2 times the square root of 10. This simplification works the same for letters for variables as well. So let's first notice that if we have the square root of 3b cubed times the square root of 18b, we can actually throw all these terms together under the same radical. This is a square root, this is a square root. So we can make this the square root of 3 times 18. 3 times 18 is 54. B cubed times b to the 1 is b to the 4th. Remember, when you have base to a power times base to a power, you add the powers. Now, I need to look and see if there are any perfect squares in here that I could pull out, because I cannot leave behind any perfect squares. I can leave behind things that aren't perfect squares, but no perfect squares can be left behind. So I look inside this 54. Are there any perfect squares that are factors of 54? Well, if I break down 54 into 9 and 6, that I can find. So 3 squared, or 9, times 6 is how I can think of 54. How about b to the 4th? It works very similarly. I can think of b to the 4th as b squared times b squared. Now I need to pull out what can come out as perfect squares and leave behind the trash. Again, these maroon notes, those are just notes to myself. I'm not actually doing anything, I'm just thinking of these things in broken down form. Now I'm about to take this radical here. Now I'm about to take this square root action on all these things. If I take the square root of 3 squared, it is 3. You're done. If I take the square root of 6, you're going to have to be left behind because you're not a perfect square, so you're going to be left behind in here. The square root of b squared is b. The square root of b squared is b again. And the 6, like I said, is left behind. Clean this up for me. 3 times b, that's 3b squared times the square root of 6. That is the simplified form of this expression. I have not left any perfect squares in the radicand. I have not left any perfect squares behind. I've just left this trashy little 6 here, okay? Let's take a look at number 3. Are there any perfect squares within this 125? There are. There's a 25 in there, right? It's 25 times 5 is 125. So a 5 squared, or a 25, times 5 is how I'm going to think of this. Are there any perfect squares within 45? There are. There's a 3 squared, or a 9, times 5 within there. Again, these maroons are they're just notes to self. I'm not actually doing anything, I'm just thinking of these things as perfect squares and not perfect squares. Now I'm going to take the action of this square root. Now remember, this negative 3 was here to begin with. So this negative 3 is sitting out here waiting to be multiplied by anybody that comes outside. Take the square root of the 5 squared, pull it out as a 5 again. That gets multiplied by the negative 3 that was already there. Square root of 5 squared is 5. Square root of 25 is 5. And I leave behind this imperfect square root of 5. I'll take care of this in a moment. Plus this 4 that was already here. I take the square root of what I can. The square root of the 3 squared is 3. I'm going to multiply that 3 by whatever was outside. And then leave behind that square root of 5. Now, let's take these actions that I know how to do. Negative 3 times 5, since those are outside the radical, I can multiply them together and make them negative 15 times the square root of 5. Positive 4 times 3 is a positive 12 times the square root of 5. These numbers are outside the radical, so I multiply them together. Now, these are like terms. I can combine these. There are negative 15 square roots of 5 and positive 12 square roots of 5. Since these are exactly the same, I can combine them. If I have negative 15 of them plus 12 of them, I have negative 3 square roots of 5. So these skills here of simplifying these radicals will be practiced. The best thing you can do to help yourself with these practices is to remember the values in these charts. You should memorize all of these so that you have them ready, so that when you see big numbers, you can break them into the factors that are useful for you. Remember, the square root of 64 is 8. The square root of 81 is 9. The square root of 225 is 15. The square root of 1 is 1. The square root of 9 is 3. The square root of 49 is 7. The square root of 25 is 5, right? All of these should be easily in your mind, and you should be looking for these numbers. You should be looking for 64s that might be factors within your radicals, within your squares, okay? Now, square root of a negative, remember, that's not a real number. That's an imaginary number, right? That's the square root of 4 times the square root of negative 1, which is I. So there are no real solutions to this. Right, so that's an imaginary number. Cubes, you should have these committed to memory as well. Cube root of 1 is 1. Cube root of 8 is 2. Cube root of 27 is 3. Cube root of 64 is 4. Cube root of 125 is 5. Cube root of 216 is 6. Cube root of negative 8 is negative 2. You can take the cube roots of negatives, but not the square roots, right? Those aren't real. The cube roots, negative 2 times negative 2 times negative 2 is negative 8. So you can take the cube roots, odd roots you can do. The cube root of negative 64 is negative 4. So again, if you are confronted with the cube root of some jumbled mess underneath that radical, you should be looking for factors, these types of factors that you can break those numbers down into, okay? Fourth roots, the fourth root of 1 is 1. The fourth root of 16 is 2. The fourth root of 81 is 3. The fourth root of 256 is 4. Fourth roots of negatives, not possible, no reals. Okay? The fifth root of 1 is 1. The fifth root of 32 is 2. The fifth root of 243 is 3. You can do fifth roots of negatives. That's a negative 2 on that one, and a negative 1 on that one. You should be looking for these factors within whatever number you're presented. Okay, you should be looking for these things. You should immediately see, oh, there's a fifth root of 32 in there that I could pull out and make it a 2. If factor trees help, you can also do factor trees. If you're presented with a number that you need to break into all the different factors and count how many cubes or how many fourths, you could use factor trees as well. All right, having those numbers in mind, let's take a look at a new skill, converting rational exponents. So we had all those properties at the beginning of today's lesson. We had all those properties from Algebra 1. Remember those? Remember those properties? If I can find them, there they are. All these properties from Algebra 1. We're going to add a new one today. The new property is this one. If you have a base to a power that's a fraction, to convert that, this is how you convert it. On the bottom of that fractional exponent, that represents your root. The top of that exponential fraction is your power. You could also write that as this. These are the same. The nth root, and then parentheses around that to the m power. Okay? I try to remember this as roots of trees are on the bottom. People in power are on top. That's how I remember how to convert these. So let's convert these, and then if we can simplify, we need to do so. So let's convert this fractional exponent, or this rational exponent. So 8 to the 2/3, what happens here? The 2 is in power, the 3 is the root. So to convert this, initially, I say that is the third root, the cube root of 8 to the 2 power. Well, I could actually simplify this, right? From that chart on the last page that I've been memorizing, the cube root of 8 is 2. We should have that rolling off our tongues. So the cube root of 8 is 2. And if that is to then be squared, 2 squared is 4. So 8 to the 2/3 power can be converted or simplified down to 4. It needs to be. Anytime you're presented with 8 to the 2/3, you need to know that that is equivalent to 4 by using these steps. If we're presented with 4 to the 3/2 power, let's convert first. Remember, 3 is in power, that's on top. 2 is the root, that's on bottom. So we're taking the square root of 4. Remember, square root, if we don't have any number here on the shelf, we assume it to be 2. So the square root of 4 to the 3rd power. What is the square root of 4? That's 2. What is 2 to the 3rd power? That's 8. So that is 4 to the 3/2 simplified. That's how we convert these rational exponents. Now remember, if you have a negative exponent, what did we say at the top of today's lesson? We said negative exponents mean we take 1 over that exponent, that positive exponent. So always if you see a negative exponent, the first thing I want you to do is say that needs to be on the other side of a fraction. Now keeping that on the bottom, keeping that 1 on top and this on the bottom, let's convert this rational exponent. This is a 2 root and a 1 power. So a square root to the 1 power. What's the square root of 9? That's 3. What's 3 to the 1 power? That's 3. So our final answer is 1 over 3. Remember that you put this on the bottom of a fraction to begin with. Don't forget that. A lot of folks, I still see you writing your final answer as 3 because you did so much work down here you forgot that it was on the bottom of a fraction. So do yourself a favor and keep track of the fact that you put this on the bottom of a fraction to begin with. So the answer to number 3 is 1/3. Number 4, again, the 3 is the root, the 5 is the power. So the 3rd root of 8 raised to the 5th power. We should be getting really good at these. What is the 3rd root of 8? We should immediately think that is 2. And what is 2 to the 5th power? That's 32. You should have those rolling off your tongue at this point. Or very soon. Number 5, we have another negative exponent. So the very first thing I want you to do is think of this as 1 over 32 to the positive 3/5. Now I want you to say, all right, this is now 1 over, which one's the root, which one's the power? The 5 is the root, so 5th root of 32 raised to the 3rd power. What is the 5th root of 32? You should know that the 5th root of 32 is 2, and that 2 to the 3rd power is now 1 over 8. Please don't forget that you did all this work. I know you did all this work on the bottom, but don't forget that the first thing you did was put it on the bottom of a fraction. So your final answer is 1 over 8, not just 8. 1 over 8 because of that negative exponent. Number 6 does not have a negative exponent, so we don't have to put it on the bottom of a fraction. We just have to take this 2 as the root, so the square root, and raise it to the 5th power. What's the square root of 16? That's 4. What's 4 to the 5th power? You may not have memorized that. That's fine. You'll have your calculator. 4 to the 5th power is 1024. Mostly we want to make sure that you understand how to do these conversions. Number 7. Think about number 7. Think about what you'll be doing here. Number 7 has a negative exponent, so the first thing you should think about doing is putting this on the bottom of a fraction. Put this on a bottom of a fraction, so 1 over 64 to the positive 2/3. Alright, now that you've done that, let's go ahead and make use of our new skill of converting these rational exponents. So this is now 1 over the 3rd root of 64, not the square root, the cube root of 64 raised to the 2 power. Be careful on that. The bottom was the root. What is the cube root of 64? The cube root of 64 is 4. Okay, square root of 64 is 8, I know that. But the cube root of 64, that's 4. So again, we're all operating on the bottom of this fraction. So 4, and then of course to the 2 power. So my final written answer on this is 1 over 16. Okay. Number 8. Let's look at number 8. There's no negative exponent here, so I'm not putting anybody to the bottom of a fraction, so I simply take the 4th root of 81, the root is on the bottom, the 4th root of 81, whatever that is, raise it to the 3rd power. Hopefully you remember from the chart on the previous page, the 4th root of 81 is 3, because 3 times 3 times 3 times 3 is 81. So the 4th root of 81 is 3, and then I raise that to the 3rd power. 3 to the 3rd is 27. Number 9. You can certainly convert this to the 8th root of 1 to the 7th power, but what is 1 to any power? You should remember this. 1 to any power is always 1. Doesn't matter if it's a rational power or not. 1 to any power is 1. Or you convert this to the 8th root of 1 to the 7th power, you'll still get 1. Okay? Alright. Here we don't really have a ton of notes for you to take. We just want to explain something that happens when you have the square root of a variable to the 2 power. So, in short, we want to make sure that whenever you have the square root of something like x squared or a squared or b squared, the square root of something squared, you know that to be x, right? The square root of x squared is x, but you need to write this as the absolute value of x. Or you need to indicate that it's x as long as x is greater than 0, greater than or equal to 0, right? Because of course that's what absolute value means, right? That means you're spitting out the positive only values of this. The rest of this page is a proof of that, okay? The rest of this page is a proof of that. So if you're fine with just memorizing that if you're ever taking the square root of x squared, you need to put it either in absolute values or indicate that it's that's a positive number. That's fine, but the following is the proof of that. If you have the square root of 4 squared, that's the square root of 16, so that's 4. So clearly, the square root of that x squared, or that 4, was x. And the same thing happened when it was 0. But think about it this way. So in this case, x is 4. In this case, x was 0. And everything worked out as expected. We made the square root of x squared equal to x with both of those. But take a look at this. What if x was negative 3? Well, the square root of negative 3 squared. Negative 3 squared is 9. The square root of 9 is positive 3. So in this case, when we took the square root of x squared, we did not end up with our original x. We ended up with the positive version of it. So that's a really quick proof. That will only happen with our even roots. We don't need to worry about it when it's an odd root. And below, of course, is the further proof of that. So for even roots, squares, fourth roots, sixth roots, etc., we need to accommodate for this. So absolute values or x is greater than 0 notifications. Alright, so that's just a quick special case, special rule note there. Let's get back to a little more practice before I set you on your way for independent practice. Alright, we're going to combine some skills here with both variables and real numbers. So let's start with numbers because those are a little easier to grasp. Square root of 8. Can we take the square root of 8 cleanly? We cannot. We could take the cube root of 8 cleanly, but the square root of 8 does not turn into a nice pretty number. We need to pull out of 8 any perfect squares and leave the trash behind. I need to think of this 8 as 4 times 2. 4 is a perfect square. So I need to think of this 8 as 2 squared times 2. Again, that little maroon is just my note to self. So that when I simplify this, when I simplify the expression, I take the square root of 2 squared and make it 2. And I leave behind the trash. So I've taken the square root of 2 squared and made it 2, and I leave behind that leftover 2. So you need to reduce the square root of 8 down to 2 times the square root of 2. Never leave square roots of 8s in your final answer. Similarly, I take a look at 18. I can't take the square root of 18 cleanly, so I need to think of this as 3 squared, or 9, times 2, right? 18 is 9 times 2, and 9 is the perfect square I was looking for. I need to find factors of 18 that are perfect squares. I found a 3 squared in there, and I'm going to take it and run with it. This is my note to self. Now I'm going to take this action. Square root of 3 squared is 3. And I leave behind the square root of 2. So that is simplified down. Square root of 40 we did in our first part of the day. So remember this was 4 times 10, or 2 squared times 10. I took the square root of the 2 squared, and I left behind the 10. So that's just a quick repeat. Number 13, let's move into the realm of cube roots. Cube roots. Are there any cube roots that live within 16? Is there anything to the third power that is a factor of 16? You should find a 2 to the third power, right? 2 to the third is 8. 16 can be broken down into 8 and 2. Why did I choose to break 16 down into 2 cubed and 2 instead of 4 times 4? This isn't a square root. If I took the square root of 16, I would care that it was 4 times 4. But right now, I'm not looking at square roots, I'm looking at cube roots. I need to find perfect cubes that are factors of 16. So again, having that table memorized of all the perfect cubes will help us get there faster. If you've memorized that 8 is a perfect cube, it's 2 cubed, you can jump right to it by looking at 16 and thinking, there's an 8 in there, there's a 2 cubed in there. So let's go ahead and take care of that. Let's take the cube root of 2 cubed and make it 2, and leave behind the cube root of 2. Number 14, we're looking at fourth roots. What fourth roots are inside of 64? What fourth roots are inside of 64? Well, 16 times 4 is sitting in there. So 16 times 4, or 2 to the 4th, times 4, lives within 64. Okay? So 2 to the 4th, or 2 times 2 times 2 times 2, that's 16 times 4. I'm going to take the fourth root, and again, I'm looking for things to the fourth power because I'm trying to take the fourth root of them. The fourth root of 2 to the 4th is 2. And I leave behind the fourth root of 4. If any of your final answers in any of your work simplify down to the fourth root of 64, don't leave this in your final answer. Make sure that you take that 2 out. cube root of x cubed. If you need to, you can think of this as x to the third raised to the 1/3 power, if that helps you do these. Or if you can see that an x cubed, when I take the cube root of something x cubed, it equals x, you can jump right there. But if you need to think of this as I'm taking x to the third to the 1/3 power, 3 times 1 divided by 3, that just ends up being x to the 1. So either way you want to think about it, that simplifies down to x. No absolute value needed because it's an odd power. 16, let's convert this. Let's go, instead of going from rational exponents to this radical form, let's go from the radical form to the rational exponent. Power on top, root on bottom. We can actually simplify this. We can simplify this down to x, and if you want to think of this as a mixed fraction, it's x to the 1 1/4, right? Or x times x to the 1/4, or x times the 4th root of x. So in these last couple, we were just simply trying to show you different ways to think about these. If instead you want to think about this x to the 5th broken down into an x to the 4th times an x, and then take that 4th root of x to the 4th and leave it as x, and leave behind the trash of the 4th root of x, you'll still get there, okay? So you can either follow the maroon path and reduce your fractions, or you can do the breakout path. You can break them out to things to the 4th power and pull them out individually. Either way is fine, whatever makes sense to you. I prefer the breakout path, so that's how I'll do these last couple. Cube roots, I'm looking for things to the 3rd power. When I see 27, I immediately think of it as 3 to the 3rd power. And I get excited because the cube root of 3 to the 3rd is 3. When I see x to the 9th, if you're a fraction person, like in number 16, how we showed in maroon, if you're a fraction person, you can think of that as 9 divided by 3, or x to the 3rd. If you're a breakout person, you can think of it as x to the 3rd times x to the 3rd times x to the 3rd. Breaking it out helps me see how many are coming out and how many are staying behind. In this particular case, everyone's coming out. I'm taking the 3rd root of a bunch of stuff to the 3rd power. So the cube root of 3 to the 3rd is 3. The cube root of x to the 3rd is x. The cube root of x to the 3rd is x. The cube root of x to the 3rd is x. I'm going to clean this up and make it 3x to the 3rd. Again, if you were a fraction person, you would have gotten there a little quicker. You would have said the cube root of 27 is 3. And x to the 9th over a 3rd root, 9 divided by 3 is 3, x to the 3rd. I'll do the visual though. And our final example of today, 32. Can you take the square root of 32 perfectly? Was the square root of 32 on our chart of things that we memorized? It wasn't, but there's a factor in there that was. What's the biggest factor of 32 that's a perfect square? Again, having these memorized will help you think of these quicker. You should realize that 32 can be broken down into 16 times 2, right? 4 squared times 2, 16 times 2 is 32. And that 4 squared, that square root of 4 squared, or square root of 16 is what we'd like to see. Now, this x to the 4th, I'm going to do this visual breakout method. If you want to do 4 divided by 2, that's fine. But I'm going to break this into x squared times x squared, because I want square roots of things to the 2 power. And then I'm going to break out the y to the 5th as follows. There's a y squared in there, times a y squared, times a y, let's just write in this 1 just for reference sake. 2 plus 2 plus 1 is 5. I tried to get as many y squareds as I could because those are coming out with me, but this y to the 1 power is being left behind. And again, the green is just my note to self. I'm not actually doing any square root work. I'm just breaking it into things that I can take the square roots of. So let's do that now in this step. The square root of 4 squared is 4. 2, you're going to get left behind. I'll talk to you in a minute. Square root of x squared is x. Square root of x squared is x. Square root of y squared is y. Square root of y squared is y. Y to the 1, you're not nice and clean. I'm going to leave you behind. Now I'm going to go capture the things I left behind. That's a 2 and a y to the 1, or just y. Let's clean up our work here. Let's make this 4x squared y squared times the square root of 2y. That's our final simplified answer. Again, if you had gone from the x to the 4th, if you had gone straight to 4 divided by 2 is x squared, that's completely fine. If you're comfortable doing that, that's completely fine. But I will show the visual for those of us that need to see it broken out. Always simplify down in your final step. Always combine your terms into these powers here. All right? Go ahead and try to work on your independent practice 3 and let me know if you have questions.